Thanks for coming to our presentation today. We're very happy to have Anais Moller joining us. She's a researcher at CNRS in France. She has a wide range of interests, but I think most relevant to the ISSC and to our discussion today, she is one of the PIs of Think, which is a broker for LSST that's under development, and she has general interest in the use of machine learning in cosmology and the study of transients. She's a member of not only the ISSC, but of DESC and of TBS, heavily involved with LSST. I think this is going to be a great opportunity to learn more about this area. She's going to speak about Bayesian neural networks in statistical analyses towards interpretability. And I'll just add that as usual, we like to keep this interactive. Please, if there are questions, you can post in the chat. Or I'm assuming you're okay with being interrupted during the talk as well. Yeah, with questions. Yes. So yeah, we try to keep this interactive. Yeah, so take it away. Thanks a lot.
Okay, thank you for being here and inviting me to talk. I'm gonna talk about something that interests me a lot, which is how can we use machine learning in our statistical analysis. So I'm gonna start with a presentation that hopefully you will see the screen now. If you don't, please let me know.
Looks great.
Okay, so the title is Bayesian neural networks in statistical analysis towards interpretability. The towards is because we're not there yet, and Bayesian neural networks is one of those clues. And I'm going to give you a practical example with a code that I wrote that is super innova, because it's easier for me to work with an example that I know pretty well and how I tune it up. So I work in Clermont-Ferrand, as you may know, in the middle of France. But today, a little bit on the motivation to start. So when I talk about statistical analysis, I usually center myself in two things. I know there are much more, but one of them is cosmology and one of them is astrophysics. And in between both of them, there is supernova cosmology. If you haven't seen this video, I love it. I hope that you can see it. It's a supernova exploding in a galaxy. So supernova are stellar explosions. They happen in galaxies, and their particularity is that their brightness rises and then fades away. The whole point is that there are many types of supernova, but for cosmology, the most standardizable is type 1a. And the problem with cosmology right now is that we're systematics limited. What does that mean? It means that our errors are the ones, the things that we don't understand or we cannot characterize well enough are the ones limiting our constraint of the expansion of the universe and therefore dark energy, our understanding of that. So what is going on with classification now in supernova? So usually we classify the types of supernova using spectroscopy, but that's limited because you probably know already there's no many resources to do a spectroscopic characterization, and also because these transients last a short amount of time, you cannot wait a year to actually get the classification. So nowadays, we do what we call photometric classification, which basically we just take this variation of brightness against time, and here is what we call a light curve. So that variation in different filters, I don't remember which ones these are, but this is a type 1a supernova, for example. And then you use selection criteria, and most of the time machine learning algorithm, to select the supernova. So below you have a box of a lot of people that have worked to develop classifications algorithms. And the whole point here is what we want is to exploit better our samples and also to do statistical analysis. So what I'm basing today my talk is in SuperNova. So it's an open source photometric classifier. The whole idea is that we just input what we get from telescopes like LSST, so photometry, fluxes against time, and then you output a classification probability. So why I'm going to talk about a supernova? Well, it's a classifier, of course. It's based on recurrent neural networks, which means that you can get a classification at any time step of the light curve. And I have different architectures, so I can compare one with the other. So I can tell you what's the difference between the Bayesian ones with the standard vanilla RNNs like LSTM or GRU. Now, of course, classifiers are important to have a large accuracy. And for example, early classification, which is with only, I don't know if you can see my mouse. Can you see it?
Yeah, we can see it.
Excellent. So one of the challenges that we have in machine learning classification for these type of transients is to get a classification with a handful of photometric points, which means a couple of measurements. And this is important for brokers, like I think, but also important to other teams that want to find things quickly. So of course, you can have very good classification accuracy with this code, for complete light curves and actually incomplete. And you can have purities that are equivalent to those that we expect from a spectroscopically classified type 1a supernova. So basically, with all the algorithms we have been developing, we are already getting to the purity we get from spectroscopy, but getting larger samples. So what is next? So to give you an idea of first the volume that we can get, I'm gonna give you an example from the dark energy survey. So this is preliminary. So this is the different fields of the dark energy survey, and we have 5 years of data. And what's gonna happen in this video is on the red part, you're gonna have the 3-year sample, and in the blue part, you're gonna have the 5-year sample, which is photometrically classified. So you should be able to see all the supernova that year by year we can get. And you can see that we can exploit much more the data we have in these cosmological surveys. And this will be the same case for LSST. Or the other example I wanted to show you is in brokers, and in this case in Think. And you can see on the left plot, if I can move my mouse back again, up to the left plot, because I cannot move the mouse anymore. There is a light curve and the classification probabilities. And you can very early on see that it has a high probability of being a type 1a supernova. And such an early thing that you can see that in the right histogram, our medium classification correctly of a type 1a supernova is -5 days before the peak light, which means you can trigger spectroscopic follow-up when it's the brightest, the object. So this is a type of applications that we're searching when we do photometric classifiers for supernova. So apart from getting a bigger statistics and getting early classification with partial information, so we can trigger follow-up if we want or trigger further studies, what else do we want? And this is basically the topic of my talk. I want a robust method, and we want something that is meaningful uncertainties for our physical analysis. So I'm going to start with a short review of uncertainties, which is basically what we don't know. So we can classify uncertainties in 2 ways. One of them is what we call aleatoric, which is basically due to the random nature of the observation, how we get that data, basically. But most importantly, it cannot be reduced by greater understanding. So if you have bad weather in your telescope that day, and you have a point that has a huge error bar, is by understanding that there is bad weather, you're not improving that measurement, basically. So it's kind of it's just the errors that we usually think about our measurements. So if you want more information, there is a very good review that I cite on the top from Charnock, Perrault, Levasseur, and Lanus that appeared this year, and I put the archive there. So they talk about this uncertainty, but they also talked about the other type of uncertainty, which is epistemic. And what is epistemic uncertainty for us? It's the lack of knowledge about the underlying model. So what does this mean for a neural network? For example, how we construct that neural network, the architecture, the way it's trained, so training sets, parameters, the cost function that you use. So it's the ignorance about the model that generated the classification. That's what I'm gonna talk today. Is what we don't know about this model that is providing us a probability of this object being a type 1a supernova or not being a type 1a supernova. And of course, this is a very simple example, but there's a lot of questions that we want to answer with this simple example. We know in machine learning that we don't have representative training sets, especially in astronomy. Who has a complete knowledge of the things that you're searching for or trying to veto against? We know that there are anomalies, out of distribution events. How do we find them or reject them? How do we know that the probability that is given actually works with these weird things? And overall, we want something that is bias-free because systematics, we want to reduce those systematics, and we want to have a meaning for those uncertainties, an interpretation. So I wanted to start this with an example of a classification. So this is the the Make Moon dataset. You probably have seen it in scikit-learn in all the tutorials. So let's say I have a training of that Moon dataset. So I have my blue class and my red class, okay? And it has a noise, of course. And I train an algorithm to classify my points with this left sample. Now, I give it this trained sample to a new sample that has kind of the same noise, and I ask her, well, classify me, give me the probabilities of this object belonging to one class or the other. And you can see most of the objects are correctly classified when there is blue and when there is red. However, you can see that I circled in colors some objects, and that thick line represents the objects that were misclassified. So the objects circled in red should have been in red, but they're actually classified in blue and vice versa. And this happens because the accuracy is not perfect, and also because this is a toy example. But the accuracy will never be perfect. We will be overfitting if that will happen. But if you increase the noise, which is not something that is completely out of our minds for astronomers, because we don't know all the diversity of our objects, you can see that the objects start to being misclassified much more. And in particular, what I want to highlight is this right corner on the top. You can see that you have a super high probability of these objects being in the blue class, but they're really in the red class. So what's happening here? Basically, the classifier learned linear separation or something like that. And then it will say, well, this is 100% the blue class, but it's not a blue class because you have never seen an object in actually that part of the parametric space. So how can we deal with this? So now below, I'm going to show you exactly for the same classification, their uncertainties. And when I talk about uncertainties, I mean, if you take a distribution of probabilities for each classification, what is the spread of it? And you can see that on the top right corner of the plot in the uncertainties, where the objects have really high probability of being classified as blue, they have actually really high uncertainty, because the high uncertainty is like beige and the low uncertainty is brown. And this is a type of information I think we want to know, but it's not very easy to get. So there are different ways of getting this. But I'm going to talk about Bayesian deep learning as a solution for this. Okay. So
Can I
the
ask
one
a
of it,
question?
yes, go for it.
I'm sorry, because you said that there is a high probability of the object belonging to the blue class, but at the same time they have high uncertainty. So how is that a high probability of belonging to that class if they're very uncertain?
Excellent question. Well, you usually take a median. So if you have a distribution of probabilities, you take the median probability, no?
Yes.
So you can use that as your probability, and then the spread of that distribution will be your uncertainty. So that's what I'm using here, actually.
Okay.
I basically get many, I get a lot of classifications for the same object, and I see its distribution and its spread. But you need like a number to characterize the probability. So usually you use median probability. Well, you could use mean, but mean is not really good for outliers. I said, does this make sense?
Yes, yes.
Excellent. Because I'm going to talk a lot about this later on, so it's great that it's clear up. Thanks for the question. So now I'm going to talk about Bayesian deep learning. The 101, very in rough terms, is when we do a classification, what do we want? And this is normal neural networks. So we want to have a classification, which I will call Y, from a given set of data, X, given some weights of my network, okay? And then I'm gonna minimize some of them. So negative log likelihood, usually you have some standard ways of getting that network trained. Now, when you go to Bayesian neural networks, it's the same idea, but instead of getting the weights as just a number, you have like a distribution of weights, okay? And that's what you're searching for. Now, the big problem with neural networks and the Bayesian part is that this posterior that I circled there is intractable for deep neural networks. So you have to do something different that we call variational inference. Basically what you do, well, I cannot get the posterior, but I can define a variational distribution which approximates this posterior. And then when I train, I'm gonna minimize the distance between these two. So variational inference is something very well known in the Bayesian neural network community. And from there, you can enter into a lot of different ways of doing Bayesian neural networks. So I'm going to talk about two, because those are the only two ways I have actually implemented. So it's how do you approximate that variational distribution? I added a third one on the bottom, which looks pretty promising, and I'm waiting to play with it soon. But I'm going to talk about MC dropout and Bayes buyback prop. So how does an MC dropout works? So hopefully you can see the left figure, the little colors. So if you have a neural network, and this is an RNN, for example, you will usually put some dropout to regularize your network, which is basically dropping a percentage of the network weights to make it more stable. So each of the left, so the first figure, the one to the most of the left, you can see that each of the arrows represent a different type of dropout, okay? So you can see there is a different dropout going in from the X, which is the data, to the Y, that is the output. And in the recurrent neural networks, remember that you go through time as well, which is the right, the arrows that go to the right. You also transmit that information, and it changes the dropout in each of these not layers, but inputs. Now, the variational RNN, the idea is that you basically use the same dropout in the deep sense towards the output and in the time sense in our case. And that's what represents the arrows in the same colors. So this is something that you can see the paper from Gal and Gramani, and this has been applied to astronomy. I put some reference below. Most of them has been in regression. So you basically evaluate the output of, for example, strong lensing, or in the case of Walmsley is from an active learning loop, if it's useful to use this type of Bayesian neural network. Now, the other one I'm going to talk about is another method that is called Bayes buyback prop. Basically, the idea roughly is instead of having one weight at each of the layers, you have a distribution of weights, okay? And then you sample from this distribution of weights, and you adapt the distribution as you train your network. So it's two ways of getting Bayesian neural networks, where you're gonna get basically, as I said, a distribution of classification probabilities, where I'll get the median to be the probability and standard deviation of this distribution to be the uncertainty. And you can do this as well with the SWAG method. So I'm going to talk about 3 cases where I tested these Bayesian neural networks in 3 subjects that interest me. How to get calibrated predictions, which means, do I believe what I'm getting out? The second one is addressing representativity, which is a problem that we have in astronomy. And the third one, also a problem that we have in astronomy, is how do we deal with out of distribution events or anomalies? So I'm going to start with the first one. So what is calibration? So for example, when you want to select a type 1a supernova sample, what you do is, well, I'm going to classify my light curve. And this classification is going to give me a probability, which you see in the bottom panels of all the light curves. So red is the classification probability of that being a type 1a supernova. And what you usually do is that you put a threshold, and that's the beautiful thick red line that I have. So what it means is everything that has a classification probability above 0.5, for example, is selected as a type 1a supernova. So this will happen for the RNN on the left, as well as the Bayesian RNN to the right, where you can see not only the classification probability, but the distribution of it. And that's what you see in the shadow regions. Now, if you see the histogram on the right, it's not exactly the same classification, but I just wanted to illustrate you that you can illustrate the classification probability as this 2D plot, but also as an histogram, because I'm going to use it later for some explanations. Now, of course, if you use these classification probabilities and you see that they are not actually saying what you want, you can change the way that you use it. And this has been used in some of the cosmological analysis with supernova. But one way to check this is what they call reliability diagrams. And this is not a new idea. This is from 1983, the first paper. The idea of this is basically you get the fraction of positives in the y-axis against the mean predicted probability. What does this mean? Let's say you have 100 events with probability of being a type 1a 0.5. This means if you really knew the truth, you will be sampling from 50 will be type 1a supernova and 50 will be other, which means that you live in this diagonal line that I put in the center of the plot. So that will be a perfectly calibrated algorithm, which means if I cut at 0.5, I will have 50-50. If I cut at 0.9, I will have 90% type 1a and 10% other stuff. Now, the issue with this is algorithms are weird and training sets are weird. So you can check this. So this is for supernova using 4 different algorithms. So I'm going to take you through this. So the first one is a random forest, which is not a neural network. It's the red line that you can see. It looks like a sigmoid. The second one is a variational. So variational should be here, MC dropout. Sorry, it's a naming that I forgot to change. MC dropout will be in orange. Base buyback prop will be in blue. And in purple, it will be LSTM recurrent neural network. So I use the same training set and validation sets for this plot, which means what you're seeing as a difference is the algorithm. And this is really important because if you train your algorithm right now with this training set and you train another one, you may have different cuts in the classification probabilities that will mean the same purity or the same percentages. And I think this is something we need to start checking. And in particular, this shows something that has been known for a while, that some algorithms have a pathological behavior, like the random forest with its S shape. Of course, if you know this, you can correct it, so you can have it all in diagonal. But this is important as well, not changing only algorithms, but keeping the algorithm the same, but changing training sets and validation sets. So you may have a difference. So if you have different generations of a machine learning algorithm, you should look into this. And this is like the first message I wanted to go through. And also that Bayesian neural networks seem to be better calibrated than other networks with exactly the same training sets and validation sets. Now, I'm going to go to another issue that we are interested in astronomy, that is representativity. So we know that the tag data sets are small. For supernova, maybe a couple thousands of supernovae. they are biased because we have only seen the brightest, or because we were looking at this part of the sky and things like that. And you use this known supernova probably to create simulations, to train and to benchmark your classifier. So what does this mean really, like in a practical sense? So you have a simulation and you have a simplistic view of one of the properties of your supernova, for let's say the peak brightness in the filter I. And this simulation, you believe in it because that's the best that you have right now of understanding, and you train a classification algorithm with it. Okay. Now, the data you get from your telescope may have the same range in the distribution of this property, but it may be slightly different, okay? But you still use this simulation to classify that data, okay? So some people have already seen for the supernova case, type 1a versus non-1a, that accuracy decreases when you see this. And I'm probably not citing everybody, so sorry for that. But this is something you can see an effect in the network. And now you want to say, well, what do we do? Well, either we improve our training sets, which is a humongous task, but we need to do it. But we can also search for robust methods. And there are some methods that have been published about improving this. And I'm missing also some people. I'm sorry for that. So with Bayesian neural networks, what can we do? So I wanted to see if it understands that there is a problem of representativity. So what I did was I trained two models. One was trained with a simplistic simulation, that yellow simulation, and one was trained with something that resembled more the data, okay? And both of them, I implemented their classification in and the blue distribution, let's put it that way. So what I have seen with the Bayesian neural networks here is that accuracy changes really slightly, that I don't see that decrease that we see with other types of networks. So that median probability is really not indicative. But what we see is that the non-representative models, which is model number one, gives in average larger uncertainties in classification. So this is what I represent very cartoonish here on the lower right. So basically, instead of having a probability distribution that is very thin, we have something large. And of course, this is cartoon because the probability distributions are not symmetric, but was just to illustrate a little bit how that works. Now, one of the questions that we have found is, okay, in average, it gives larger uncertainties. This is not true case-by-case basis. And most importantly, MC dropout and Bayes by backprop give very different amplitudes or uncertainty sizes, okay? And this is all linked to how you initiate your network and how you understand these networks. So all of these methods are quite new. And I think a lot of the benchmarking that has been done, especially in the machine learning community, is actually with very toy data sets, and astronomical data sets, as you all know, are much messier than many of these. So this is for representativity. I think it's promising the Bayesian neural networks in that sense. But now I'm gonna go to my last topic, which is out of distribution events. And this is the typical cats and dog problem. So you train with cats and dogs and you want to classify a zebra, which is basically in astronomy will be, for example, you're training with supernova likers that are shown in the left, and you give, because we are working with a broker, for example, for LSST, you give variable stars or something completely weird. So what does happen with the network, okay? What happens with the network, what you would like it to happen usually is, we would like that if I classify this thing that doesn't look like a supernova, you will have a low probability for any class. Let's say I'm classifying in 7 classes, and none of them will be a high probability. But what happens as well, which is sad, is that overconfident exists. It will give you an overconfident prediction that this is 80% probable, I don't know, a type 1a supernova. And why does it do that? It's because it hasn't understood all of the classes that you train with, and it will just take the most difficult class to learn, and it will throw everything into this. So we did this exercise with Bayesian neural networks, and what we see is the following. So this is the classification distributions for these objects in 7 classes. So these are all supernova, type 1a, 1bcs, 2p's, 2n's. Well, the taxonomy is long, but there are 5 2n's. And you will see the behavior for one side, low classification probability for all of the classes, as you can see in the top plot. Or you will also see that sometimes it will give a super confident prediction, and I'm talking here about a median probability of 0.7 probably, of this object being a supernova, which is not true. However, because we are using Bayesian neural networks, we have that distribution. And the distribution can tell us stuff. And what we have found is that in average, classification uncertainties for these anomalies are increased. So larger than what we would expect for supernova that are classified. So this is interesting. This is something promising. However, again, the problem is between different methods, given the same training set and the same data set, we still have different sizes of uncertainties. So how do we interpret this? And that's not an easy question to answer. And I would love that other people jump in to think about this with me. Because I'm interested on this, and it's hard to give an answer that we can trust. And I think there's a lot of power on this. So to give you an idea of probably not, it's out of distribution, but also representativity, and my title may be misleading because it's a little bit both. I'm going to give you like a practical example. So this is something that's quite preliminary that I have been playing with. I'm playing with using different core collapse templates. Okay, so these are types of supernova that are not type 1As. These are supernova that we don't understand very well, most of them. The rates are not well known, so imagine you can find anything. So I trained a model with type 1A and a model from Vincenzi et al. 2019. And then I applied it for core collapse only from other simulation of Vincenzi 19 templates, but also Jones 17, and new templates are being created in DES with core collapse. And you can see that the accuracy actually doesn't change that much. I didn't put the error bars, but the errors are tiny. And in the lower left, you can see the median classification probabilities, and you can see the distributions don't change that much. And usually you cut, let's say, in 0.5 probability for classifying this supernova. But what I'm working with is the right plot. And the right plot shows you the uncertainty of those probabilities. And you can see that the different the template is, the larger in average the uncertainties is. But how do we interpret this? And this is a question that I am trying to solve. I can see that maybe my template is not the best for this data, and that is a useful knowledge to have, because we don't know maybe how we characterize this core collapse for this survey is different from this one, and we want to not use that template or use another one. And this is a way to evaluate this. And I think that's interesting. Now, for the one-to-one case, it's a little bit harder to talk about. So I actually have reached to the end of what I had prepared for today. You didn't interrupt me that much. Please feel free to ask me questions at the end. I think Bayesian neural networks are a promising avenue for meaningful uncertainties. We have shown that it's starting to give something that we can interpret ourselves. We have seen that they are better calibrated for classification, and also for the regression cases I showed you before from other astronomy and cosmology references. They can be sensitive to representative training sets and sensitive to anomalies. But of course, behavior and astronomical sets are different from what you will have in other machine learning communities. So this is something that sometimes we need to study much more in depth. And the different methods can provide us quite different uncertainties. So how do we compare one to the other? And this is the type of benchmarks that I'm interested now to figure out. So more work is needed. If you have questions, comments, ideas of how to deal with this, I will be more than happy to chat. So that's it. Thanks.
Thank you very much. That was great. I'll start with a question here. So I think a big part of what you're trying to say, if I understood correctly, was that these Bayesian neural network approaches can help to account for the epistemic uncertainties. Could you just maybe step back and describe in a big picture sense how that's working? So what is it about the Bayesian approach that allows you to capture that additional uncertainty that was maybe missed previously?
Okay, so that's a contentious question, because you can always say that by doing jackknifing of training sets and changing templates and things like that, you get a little bit of the uncertainty of the classification model that you get. But that's not the whole story. As you can see, there is more stuff behind. So it's not only the training set being changed that can give you that perturbations, but you want to know how the model was trained, how it changed, how the cost was written, how it changed. So you really want to test the limits, or I always think of perturbing the model to see what are their limits. And it's not only through jackknifing of the training set that you can find these. And I think that's the interesting part of this, how you can get these. I can put back the epistemic uncertainty slide. Let me put it back. It's really the underlying model that you want to get to know if your classification makes sense. So, and it's also providing you a natural way of approximating a probability distribution a posterior on this. But then again, you can read all the machine learning papers on the Bayesian neural networks approach, and some will say this is better than the other one. And it's not really clear which method is the most robust right now.
Right. How about other questions? Are there other questions that people have?
Hi, this is Tom Laredo. What priors were used for the Bayesian neural networks that you?
Okay, so we use for the, especially for the Fortunato one, I'm gonna put the slides back again so people know what I'm talking about. So there are two networks. So the first one, you basically play with the dropout. So the values of the dropout and how you characterize it, we use the same structure that they use in Galen-Ramani. But in the right one, which is based by backprop, you need to give a shape of that distribution of weights. And we simply use a normal distribution, a little bit perturbed. I can send you the parameters if you want. When we play with the initialization parameters, we realized that the size of that uncertainties change a lot. So what we did was try to tune it not only for good accuracy, but to actually try to approach the two methods. We didn't succeed. But it's something I think the initialization is quite important in this type of architectures.
So was the prior over the weights independent for different weights, or did you allow correlation in the weights?
Just a general functional form for all of them, and then you will have an epsilon that will be perturbed.
Okay, I'll have to look at the paper. I didn't follow.
Yeah, more than happy to send you the part of the code or the paper that describes it. I think.
Other questions, comments?
Can I ask another question? I'm
Sure.
Maurizio Paulillo, by the way. I was wondering, all the example that you showed are supernovae or variable stars. What if you have something like an AGN, which can have completely random variability, and so it's really hard to get a pattern out of that? How bad is this case to treat?
Well, I haven't tried with AGNs yet in a thorough way. So we have started, I am part of the Think broker. So we are applying these type of networks to the whole CTF public alert stream. And I started checking a little bit the known AGNs, what happens and things like that. But I cannot tell you exactly in average what's going on right now because I haven't done the analysis. What happens is two things. Is the two things that I told you about out of distribution. Either I have a very high confidence that this is a supernova, which happens many times if you think about it, because you have in the alerts, you have only like the last month of data. So sometimes AGNs may have a variation that looks like a supernova in that part of its periodicity, well, semi-periodicity. But sometimes you get completely, no, this is not at all a supernova with really high uncertainties and very low probabilities. So you get both behaviors, which I haven't characterized in average yet. But this is something that I want to search for. So if you have some test data you want to try it with, I would be more than happy to try to figure it out.
Thanks.
No worries.
So can you say something about computational costs? If we're doing this at LSST scale, what are the issues there?
Yes, so well, neural networks, if you have a GPU, is quite fast, especially when you're just evaluating if you have trained your algorithm. What happens with these Bayesian neural networks is that you sample either from the distribution of weights that you have in the photoanalytic behavior or different passes of the MC dropout as well. And it will reduce your performance. So if I remember correctly, I can give you the numbers exactly. We get a reduction of the performance, the speed. Let me search the numbers because I know I have them somewhere. So here, share screen up. So this is the paper of this method. So you can see that the number of supernova per second for a traditional RNN could be 20,000. Well, now for the Bayesian ones, you will have an order of 2 orders of magnitude slower. So for LSST, I think this cannot be, for example, a broker like the 30 seconds processing. This can be something that you can do within a day. But I think if you just want to know the uncertainty, then maybe you can wait some couple of hours so we can process all the alerts.
Yeah, that definitely makes sense.
So I think Bayesian neural networks is an extra thing. It won't give you a very different classification. As you can see, it didn't change much the accuracy. It's giving you something extra.
Yeah. Okay, I just want to make a quick comment here that this recording, along with others, will be available. I'm just going to post it into the chat here before I forget. You can see previous presentations there as well. Any other questions or comments here?
Anais, may I ask a question? Eric Fogleson.
Yes, for sure.
Hi. Using Bayesian approaches for quantifying, for uncertainty quantification of neural networks, essentially, is sophisticated and seems elegant and promising in many ways. What about sort of more old-fashioned approaches? I think you mentioned a jackknife. I forgot, as an old-fashioned approach, but what astronomers have often historically done is just do Monte Carlo, creating new data sets, just jiggling their data points by the measurement errors, epithetic uncertainties because they know the measurement errors. There are many fields like image analysis of real life fields or something where there's no known measurement error. That's not the point. But in astronomy, we do have this additional information. So I was wondering, could you compare the performance of your sort of modern sophisticated approach with an old-fashioned approach, like jiggling the data points?
I love this question because this is something I'm working on. These are great questions. So I did already some preliminary tests by jiggling basically the simulations, because I can simulate in different scenarios and different templates, and to see if I get different predictions, if I have different models trained from a slightly perturbed simulations. I don't get the uncertainties I get with the Bayesian neural networks. I get an uncertainty. I'm still trying to figure out how to interpret it, but I'm still working on this. But I can see that it's not the same type of uncertainty in many cases, but I cannot answer you yet. But it's on the list of things to do. I think some people have worked with this in the machine learning area, but their data sets are very different from us. So I think it's worth it to try it with the astronomical ones.
We're very rare in statistics in general, data analysis in general, that we have the known variances to the measurement errors instead of just measurement errors that become parameters to the model. Often they're not data inputs. So I think this gives us a step up. Maybe we don't have to do some things that the, I don't know, computer vision people or economists have to do. Maybe we can do better because we know more.
Hopefully, let's see how that goes.
But do you think it's possible to, or do you feel like you are already incorporating that sort of information into the Bayesian neural network approach? Is it maybe feed into the priors somehow, or other aspects of the architecture that can capture aspects of the uncertainty that you're familiar with or that you know about?
Such as those weights, those W's?
So we didn't use any physically motivated priors for these weights. We use what the paper of the method proposed, because if you define it in very different ways, you may have problems converging. So they can be a little bit tricky to define. But this is an issue that I would love to explore, but I think it requires some serious work and serious thought, how we can interpret those priors as well, how we can use our information that we know into a weight prior, which is not the same as a prior in a hierarchical Bayesian method prior. They are quite different. So I need to learn how to do this bridge.
So the uncertainty, this is Tom again, the uncertainties that Eric is asking about have to do with measurement errors, which is something separate from the weight uncertainties that are the new piece that BNNs take care of. So a question is do the Bayesian neural network algorithms you're using actually use measurement errors in a Bayesian way? Because that's a separate layer. That's actually more kind of aleatoric, but that's separate, and it usually doesn't arise in a lot of the machine learning applications. So like, what do you do with the flux errors? How do you handle those?
So we input them into a network. So the network has the knowledge of the measurement errors. So what we get is true.
But the Bayesian approach to treating the measurement errors wouldn't use them as additional inputs. It would use them as uncertainties for the unknown true inputs.
Yes, it's true. We haven't treated the measurement errors in a fully Bayesian way. What we did was to input them as a standard feature. So when you get the uncertainties of our networks, it's true that there is some mixture here because we're not treating the uncertainties of measurement as a separate thing in a fully Bayesian way. And that's true. Then again, that's making my problem a little bit more complicated, not impossible, but more complicated. And I started easy. But this is something that I think is interesting to see how we can treat this fully Bayesian way.
Yeah, Victoria asked the same question in chat. So, yeah.
Yes, I just saw it. Thanks. Yeah, you can put it in the loss function, of course, but we haven't touched that because already training the Bayesian neural networks to understand what was going on was tricky.
Okay, this has been a great discussion. Is there any last question that anybody wants to bring up? We're almost to the top of the hour here. Any other questions? All right. Well, thank you very much for this presentation. I think it was very interesting, and I really enjoyed the discussion in your presentation. Once again, this will be posted along with the other presentations. I think we have a number of good ones there. So this will be posted there shortly. But thanks a lot. And thanks everybody for joining us.
And if you have any other questions, you know where to find me, at least in Slack. Ping me. I'm more than happy to chat more.
Great. Thank you.
Bye.
Bye.